Okay. Hi, everybody. This is Ozep. I am tired and I'm also a student, so if I get anything wrong, don't blame me. I will repeat this again. Please, if you join this call, mute yourself. Taha can mute people.
Okay, you have to give me permission.
Okay, I'm gonna give permissions to Taha so he can mute people, so it's less distracting. We're gonna go through a review. And yeah, if you have any questions, feel free to ask, but don't unmute yourself. Just type it in one of the review session questions or session questions or even call related, and I will gladly answer it when I have a moment of pause. So I've done a little bit of stuff now because I forgot to announce it, but I'll quickly go through my solutions, and we're just starting to cover the harder stuff. Right now, we're reviewing the 2018 midterm. Does anybody have any questions out the get-go, or can I get started?
I don't actually have headphones on, so I can't hear if someone speaks. So if I see you unmute, I'm just gonna server mute you right away.
Perfect.
I'm not gonna wait to see if you actually speak or not. It'll just be server muted.
Can you hear Taha speaking? Probably not. Okay.
They can't speak.
Just please do not unmute yourself out of turn. And we're live. Well, we're gonna start now. So the recording is gonna be kind of low quality because we're recording a stream. It's okay. You will have to sit through it. So right now we're just starting with the first question. I'm gonna do a quick review through this because it was covered in class, so you should kind of know. This is just a reminder. I have covered this in my midterm 1 review. So I'll give you that permission. Give me 1 second.
It's based on role. It's based on roles.
Roles? He's already the highest role.
You have its overpowers. No, I know.
Okay, I'll just meet people. It's okay. Anyways, we're gonna get started. Or you can meet people. It doesn't matter. This it's streaming the screen though, so I kind of don't want to bounce off of it. Okay, we're gonna start. So the first question is gonna ask us for 1K memory locations, you need blank address lines. The solutions are shown here. Sometimes I will scroll up so the solutions are not seen, but we're just gonna go through them. We cover this exact question in class. We have 1K memory, right? For my midterm 1 review, which I'm going to just reiterate through, I propose this equation, which is 2 to the power of n times k. And n represents number of address lines, k can represent size of word, number of bits, number of functions. So for this one, it's asking what number of address lines does 1K memory produce? Well, we know that 1K memory is equal to 2 to something, right? So 1K is represented by 1,000. So we're going to solve for that. And we know that 2 to the power of 10 is equal to 1,024. So that's why we came to the conclusion that it's 10 address lines. Does anybody have any questions for this initial one? Can you check the chat? Thank you. No, we're good? Perfect. So now we're going to go and cover the rest. I kind of just provided the solution that it's a PC counter. We know from a diagram in the annex, which is this is kind of a picture of, that this is the cycle of how you decode a instruction. As you can see here, the PC, after you decode the first instruction, you're always going to see PC is equal to PC plus 1. So that is why the PC is chosen here, because it points to the next instruction. Okay, I'm just going to speed through this because it was already covered in today's lecture. So now we have this this ALU, well, arithmetic unit. This is also covered in my review from midterm 1, but I'll just quickly iterate. You're given a series of functions or formulas, which I've written here. You simply want to break them down into its individual pieces and see what should be in this mux, which is D0, D1, D2, D3. And we concluded that since it's A0 plus B0, this first one's going to be B0, second one's going to be 0, last one's going to be 1, and then B0 primed. Perfect. So that's pretty simple. If you don't understand, please just rewatch the video that I've sent previously. Okay, now we're going to just get into it. I might as well just redo this one. Sorry for the folks who are actually live in person. I'll keep the math because the math it's very long to do and tedious. There we go. Okay. We're going to start and do question 2.1. Let's try this again. So we start with some information. We have PC, which is pointing to 3AF, and we have AC, which already contains 2EC3. This is perfect. So the first step is you see what the PC is pointing to. What is that instruction? Well, 3AF, the memory at 3AF contains 93AD. Okay, what is this instruction telling us to do? Well, we know from 15 to 12 is our instructions plus the indirect bit. And this is your address. So let's see what 9 is. Well, since this is in hexadecimal, we're going to convert it to binary. So it's going to be 1001. This is your instruction, which if you look in the annex, corresponds to add. And this is your indirect bit, which is on. Okay, what does this mean? Well, we answer the first question here. What is an instruction that will be fetched and executed? This instruction is simply add at this address 3AD indirectly. What does that mean with our overall program? Well, you go to the address 3AD. We see what is stored at that address. And if you see here, 3AD has 03B5. Perfect. So now then since it's indirect, we're going to the address that is stored at that address. So we're going to see what 3B5 has. M3B5. 3B5, we know, is storing the instruction. I will remind you guys again, please mute. 3BF is storing the instruction. And if you look here, 3B5 is going to be 3B9F. Okay, and that is what will be added to the AC. So I'm just going to zoom out. So as you see here, I kind of drew out the addition for you. The simplest way to add two hexadecimal numbers together is to convert them into binary and then do the addition, which you see here. F is 111, right? 9 is 1001, and so on. And then you convert it back to hexadecimal, which gives you the solution. So we know that the AC at the end of the day is going to have 6A62. Perfect. Okay. Now it's going to ask you to fill out the table. Since we know what this program does, we can start going to the next step. Well, PC, after you decode and fetch the first instruction, is always going to be PC plus 1. PC, we know from before, has pointed to 3AF. So now it's going to point to 3AF. It's going to be pointing at 3B0. Okay, we know that the AC has this value. What else? Well, let's start going to the address register. So the AR is the address register. This means it's going to hold the address of whatever we sent to the AC. You know, from left to right to left, the only way to send anything to the AC is through the DR, right? But what it determines what the DR contains. So the AR will have, let's see where we fetched it from, 3B5. Then the DR will have, according to left to right, sorry. Can I use that? Thank you. According to left to right. And to do AC plus DR, to add anything to AC, you must do it through the DR. So we know that the DR is going to be whatever we added to the AC, which is 3B9F. Okay, and then we have IR. IR is the instruction register, which is going to hold our initial instruction, 93AD. And we know since the indirect bit was turned on, that'd be 0. And the SC is just simply the clock, which is always 0 at the end of an instruction count. So just to reiterate, AR is an address register. It's going to hold the address of whatever you sent to the DR. DR is like the data register. So whatever any manipulation you do to the AC has to first be sent to the DR. So if you're adding something to the AC, that will be your value of the DR, the thing that you added to. Okay, and IR is going to be instruction register. It's going to hold your initial instruction. Now, does anybody have any questions relating to this? Or can I move on to more difficult things? Oh, perfect. Check the chat. Nothing? Perfect. Okay, we're going to move on. So yes, just a final check. Yeah, I'm correct. Perfect. Okay, I began to write down the code for the next question. What is the result in decimal of the operation performed by the assembly program? So I'm just going to continue to do so. Be patient with me for a second. Op2, halt 10039, opt FFA5, opt2, 0, and then end. Okay, we know from class that org is it tells you where the start of a program is. And we know this program starts at 100. So I'm just going to write the lines actually on this side. It's going to be 100. Then we just count by 1. So CMA and ink, I wrote it on the same spot. So I'm going to use a nifty tool. Does this work?
Mhm.
Oh, perfect. And I'll just fill in the rest. Okay, that's so cool. Thank you. And then I'm just going to erase this. Okay. So CMA will also be 101, ink will be 102, 103, 104. You're just going to count by the lines 105, 106, 107, 108, and then you end the program. Perfect. So now we have done like the first step, which you see here. Now, what is the memory content? I'm actually going to just slide that away because I don't need it anymore. What you truly need is the annex, because this is what tells you exactly what to put as a solution. So the first step is load to the accumulator OP. We search in this annex. We see what LAD is represented by in hex code. It's represented by 2, but usually hex code is 4 bits or 4 things long. So we find what OP is. OP references this line of code. So it's going to be 2107. Okay. We see CMA. Well, CMA already has a set code. We're going to copy that down. It's going to be 27200. Ink is going to be, we find it, 720. It's going to be add OP. We're going to go up here. Add is 1 if it's non-indirect, and 9 if it's indirect. We know this is not indirect, so it's going to be 1. And then it's going to be OP right here, 106. Store the accumulator is going to be 3, and OP2 108. Halt is just a set code 7001. So if they ask you to fill it in to a chart, let's say here, and it has 100 plus 1 plus 2 plus 3 all the way through, you're just going to copy them as they appear down this row. So it's going to be 7200, 7020, 1106, so forth, and then fill the rest with zeros. And you're also going to fill in these. So at 106, you will put 0039. At 107, you will put FFA5. And at 108, you will just put 000, and then fill the rest with zeros. Perfect. Is there any questions for that? None at all? Okay. There is stuff in call related. I'm just going to check it out. Perfect. Okay. Okay. So we're going to go to the next question, because I think that was it. I'll start explaining more things when we get to harder stuff. Like, I think the next question is actually semi-difficult if you don't understand what it is asking you to do. Okay, for this question 4.1, I honestly have no clue what it's asking. It just says examining the NX block diagram of Mano's basic computer, give a list of blocks of the data path and list those that form the computer's control unit. I honestly don't know what this means because, like, it's just telling you to copy from the back of the book, essentially. So I'm going to skip that. If somebody knows what it means and has the answer, feel free to post it in the chat. I will look at it later. So now we're just going to do 4.2. 4.2 is a harder question, but I'll break it down into simple steps so it's easy for you to understand. And it will take minimal memorization. Okay. So you have to expand the instruction list of your textbook, Basic Computer, with 3 more instructions. ASR, div, tat, as shown in the following table. Both circuits have a data path and a control unit that need to be extended. This basic computer is a simplified version of the one presented in the textbook and does not have any provisions to deal with interrupts. Okay, so the first step is you're going to make a table. And this table is going to have LDDR. It's going to have XT4. Okay, and then you're just going to do a big table in R YT3, then you have clear RZT3, and then you have SHR BT3 plus WT4. Perfect. Okay. And at the top of this table is going to be DR, and it's going to be DR, its next state. So basically, if you focus on the question itself, you know that it's only manipulating the DR. So that's what's going to be changed. And we're going to implement this change in the DR using a JK flip-flop. Okay. So the first step is you just fill in this table 0, 1, 0, 1, 0, 1, 0, 1. So if the DR is 0 and you take the command LD or load DR, which means transfer the value from the bus to the DR, you're just going to be transferring the bus at that I. This is going to be for DR I from 1 to or 0 to 15. You're going to be transferring that specific DR bus line to that DR. So its new value will be that bus line. And then you're going to do the same for the next step. And then for this, it's INR. What does INR do? It increments the DR. So we're just going to do a random sum for now, and we will explain what that means later. Okay, and then it's clear DR. So it's just going to be a simple 0, 0, and then it's shift right DR. So this is something that will need some explanation. Pretend this is your dr in terms of like a array. When you shift right, you're moving every index +1 to the next index. So this new value would be I +1. Then this one will also be shifted. So you're just shifting these values to the right. So essentially what this would do to the dr, well, it would just transform it into the dr I +1. It's taking the value of its index +1. Well, if this is like the greatest index, 0 to like 1. Well, if this is dr10 and we're focusing on dr9, dr9 will take the value of dr10. So this would be I +1. So in terms of this table, we're going to simply write it as dr I +1, dr I +1. Perfect. So now, since we're going to implement this through a JK, I'm just going to start it off with that. And this is the only thing that takes some semblance of memorization or previous knowledge. So we have an input. We're going to do input primed with D. Then we're going to do input. Then we're going to do input primed. That is how we're going to fill out this table. So using that as an example, we're going to do the first step. This is going to be bus at I. This is going to be D bus at I primed. This is going to be D bus. This is going to be bus I primed. And then we're going to move on. This is going to be, okay, oh no, perfect. This is going to be SI, D at SI primed. Then it's going to be, this is D of SI, and this is SI primed. And then you can see this more clearly with the ones and zeros example. If I can just find that. So this one for the circular, for the clear, you're gonna copy the same value at the start. And then you're gonna do D of that second value, but prime. So this 0 is gonna turn into a 1. And then you're just gonna do D of 0, and then this value would be 1. And then it's the same for the dr. dr +1 primed, dr +1. Then it's going to be dr +1 primed. Okay. So now we have to find, we're going to simulate this change. So we have to find the values of j and k for our jk flip-flop, which I'm just going to draw here to speed up the process. This is a clock. And we just need the input for k and for j. And we know the output will be the value that's in the dr. Okay. Well, we have to check where it is equal to 1 for the j. At 1, we have bus. So we know that for xt4, we write bus. Okay, now we're going to do the same. We get xt4 from here. So it's just going to be copy and paste, like t3. This is going to be si plus, this is 1, but this value is essentially 0. So it's just going to be zt3 at 0. We remove that, plus, and then it's going to be vt3 plus wt4 at dr I +1. Okay, and then we do the same thing for k, but instead we take this value. So when it's 1, it's xt4, then it's bus primed. And then for yt3, it's going to be si primed. And then for, now we actually can have the value of t3 because this is 1. And then we do the same, vt3 plus wt4. And then it's dri plus 1. Oh, sorry. dri plus 1 primed. Okay. And essentially what you do is you attach these into the input slots for the JK. And that is pretty much it. Okay, I said before that I'd explain what S is. S is the dr plus 1. So I think it'd be sufficient enough to show that you're using full adders here. Right? We know that this is just going to be cy, which is input, is equal to 1. We attach the dr at 0 here to the full adder. We input it into that line because this is just 1 unit. So we know that we're going to take that and we're going to take the next carry. So this is cy. If there is overflow, we send it to the next one. This is dr0, or this is dr1, and this is dr15. We have arrow here, noting a pause, and we just feed that into the system. So if you say this, S0 is equal to dr0 plus 1 using the system, I think it'd be good enough answer. Okay, one quick question. Is there any way to make the lines darker?
Zoom in.
Ah, okay. Makes sense. Was there anything you needed?
Can you quickly answer someone that needs that?
Okay.
It's the guy. And he's expanding the
Let me see. Okay, so this is the first half, which I'm gonna stop the recording now and then re-record, just because I have to set up something quickly. So I'm gonna stop the